Well, good afternoon. My name is Rick Wesson, and I work for a company called Support Intelligence. And I think this talk is going to dovetail really nicely with the previous gentleman. I too do a whole bunch with images, and we'll show you some movies about them. But before I get started, I'm a dyslexic person, and I'm always interested in meeting other dyslexic people, especially if you're from the Bay Area. We have some things that we're going to get started this year about dyslexic entrepreneurs, so definitely catch me in the hallway, and I'd like to meet you. So, where we are today, and this is about the challenges that we're trying, the domains you already heard about that the last gentleman, Jamie, I believe, was working against. And so on a daily basis, we're looking at millions of applications that we have to decide if they are good to run or not. We have hundreds of thousands of websites, domain names, URLs, thousands of C2s, millions of DGAs, and thousands of new YARA signatures that we got to send down to our devices. And so the problem that we have is, I consider similar to the halting problem, which is it's still hard to figure out whether or not we should run some code. The halting problem is, as Turing stated, a problem in determining when a program's going to stop. What I want to talk about today is deciding whether or not we should start a program. And so this gets into an asymmetric problem for us as defenders of networks, where we have a strategy, but it's to identify the compromised endpoints, so we end up with a whole bunch of data feeds that we put in our devices to list all the evil things that we shouldn't do or talk to. And so we use a whole bunch of biological metaphors to describe these activities, none of which work nearly as well as the actual biological equivalent. And so if our immune systems worked as well as our firewalls, we'd be all dead, right? So I got to get two concepts across for the rest of the talk. And those two concepts start with this idea of an information apex, okay? And an example of this is trying to figure out how many real voters there are in America that are eligible to vote, that are enrolled or on the voting rolls. And so if we try and count all of the voters on these rolls, we have way more than we have Americans. And so the Pew Charitable Trust and IBM got together, collected a bunch of voter rolls, and clustered the individuals. And so what happened was their data set was growing. And as it grew, and they started to cluster the individual voters, adding another voter didn't add a lot of data to the data set, right? If you have 3 rows that are all the same people, that's really one entity, not 3. And so your data set begins to get smaller as you add more data, right? It's the opposite of a hockey stick problem. And so what we want to do is find that asymptote where our data growth rate turns negative. And so the second idea that I want to get across is something that I made up. And being dyslexic, I don't know how to spell this word, but imagification, which is where we take a piece of data and turn it into a pixel, right? And so for the rest of the talk is about how we do this with applications, spam, email, anything, scaffolding, HTML. And so doing this, we can convert these data sets into images and then eventually into a 64-bit identifier that is essentially a pixel in a 64-bit phase space. So when those pixels are next to each other, the information that they're related to is similar. And so that's what we're trying to do, is find similar images, which is like what the fellow before me was having an issue with. So it turns out really hard to do with a CPU. It's very expensive in time and compute. And so we do it with GPUs. Now, this is an example of imagification, right? We can't read the data there, but our phones can. And each pixel is actually part of a data set. And this one will turn into a URL, right, for your phone. Now, what we're going to talk about, though, is a particular kind of, we're going to do something with the data. We're going to put it into something called a space filling curve. And so this is the first time I saw a space filling curve. And this is the internet on XKCD. For an example, I'm going to show you some examples of the imagification of DNA. I like DNA a lot. Everybody should. It's in every one of our cells. And this particular DNA that I'm going to show you is packed in a space-filling curve. But this is a two-dimensional space-filling curve of Ebola, which just yesterday the United Nations said that Sierra Leone is free of Ebola. Today, someone died from it. Yeah. So this is a 16 kilobyte virus that kills humans, right? And on the left, you see it in color. On the right, you see it in black and white or grayscale. So this is a Hilbert curve, and all DNA is packed, all eukaryotes. Prokaryotes don't work this way, but eukaryotes, which is basically people and animal and lots of other stuff, pack their DNA in a space-filling curve. And you can display those in either 2D or 3D. Now, the second time I was playing around with space-filling curves, it was with IP addresses. So this is the internet in a space-filling curve, and this is the virus response in 2007 to a virus. And so this is, we had sinkholed the domains that this particular virus used, and we were able to display in a simple image the representation. Each pixel here is a IP address /24. So it's 255 IP addresses per pixel, and the number of infected hosts are in color. So this is the same concept, same thing that DNA is using, space-filling curve, but this is a program. Now this program happens to like stealing your passwords for your bank's accounts. And it also had a really low detection rate on virus total. So what I'm going to show the rest of the talk about is clustering this kind of data. And we can cluster all kinds of things like web content, which has utility that you heard already in detecting phishing pages and phish verification. I'm going to show you how to do it with email in SMTP streams. And finally, it's really about safety, file safety. Can we run this program? And this is a really quick way to determine if we can run a program without running it. And so this is the first movie. I seriously hope it plays. Yes. Okay, so this is a cluster of malware. It's actually not malware. It's a potentially unwanted program that is published by a legal entity that publishes tens of thousands of these per day, so it gets through antivirus. And it takes over advertising, essentially providing ads for you. You can see the MD5s across the top of the page, and what you're seeing is how they change the code in this particular binary, where each binary is a image. I can't think of the word that I wanted to tell you there, but I'll try it again. Here is, excuse the screen grab, this is SMTP. And what you're seeing is, this is a FedWire SMTP that went out to CFOs about a month ago. And what it was doing was convincing a CFO that the Fed was going to be down for a couple of hours for maintenance, and they needed to change the time that they sent their wires to them. And so when you clicked on that, your CFO got owned. And what was happening here is you'll notice that it's a much more muted image, and that's because email is 7 bits, right? So we don't have 8 bits. In email, the only carriage return and only the carriage return and line feed happen to be control codes. And so the little black pixels that move around are the CRLFs that are at the end of the 80-byte record length for an email. You can also see the header in the top left-hand portion of the screen. and that's what moves the image around. The interesting thing here is that there is some texture that doesn't change, and that's what we leverage to identify these. Okay, so here's another movie, and this is a Trojan. And not much is going to change in this image. I don't know if you can see the couple of pixels that change near the bottom. Then you'll see the whole thing move. And so this is literally thousands of samples of a piece of malware that has a pretty low hit rate on VirusTotal. And what we're going to do is convert malware, that's what this has done, convert malware to an image and then place that image near other images because they look similar, right? It was the same problem that the previous gentleman was trying to attack, which is how do you sort these images? And so you cluster them. It's looking for similarities, right? So it's a test for similarity. Like I said, it's hard to do on a CPU, even with a bunch of cores. It's best on FPGAs. But in the meantime, FPGAs are really expensive, but GPUs are fairly inexpensive and cheap in power usage. So the CPUs are used to schedule the code that's going to run on the GPUs and manage moving data around. We were able to get our clustering times down to just over half of a millisecond per sample, right? So when you have an internet scale problem, you have to think about how much energy you're going to use. Like the previous gentleman had a strategy and it took too much time. It took too much time and his queue got wiped out. Or it takes too much time in the case of sandboxing, right? We're going to run each sample for 5 minutes. So I came up with this idea of what I call an info joule, and that is how much energy it takes to make a decision. And what we're doing is we're making a decision about whether or not we should run a program. And we want to make that decision as fast as possible in the least amount of energy. And so I came up with this idea that an info joule is a unit of information calculated in joules, but expressed as the time to calculate the information in watt seconds. A watt second is the same as a joule or a Newton meter. And so if you like this kind of stuff, there's a reference there for the idea that information is actually heat. And there was an article published on some of this thinking last year. Our best classification times were in June, and we were able to get, or actually in June, our best classification times were about 33 milliseconds per sample. We get a couple of 100,000 samples a day, and we need to get through them. And at 33 milliseconds, it took a couple of hours to get through all of those. Now, if we were to sandbox them, actually, we'll go through that math in just a second. Our most recent work has been on the Xenon Phi and the Altera FPGAs, which have been a lot of fun to work with. All writing in OpenCL, we got our operations down to about 88 RISC operations, all in integer math, which gave us a compute info joule of 0.88. So we're less than an info joule, less than one. And so if we compare that to sandboxing, we get, sandboxing is extracting features so that you can learn whether or not you want to run this program. Most people give them 5 minutes, sometimes 20 minutes, depending on what kind of counters you find. Now, if you're going to run that on a bunch of VMs, we can work through the problem of what it takes to do that for 300,000 samples, which you'd need like 625 samples analyzed per server per day on 480 servers running 100 VMs each, which is 13 racks of gear of 2U servers. And if we figure we run them 24/7 at 1,800 watts, it comes in just short of a megawatt to do that, to sandbox that many samples. And so one of the reasons I really like fractals, space filling curves are a fractal. Fractals are the kind of mathematics that nature uses. And nature uses that math because it is a very special place in design values. So usually you hear your boss, or maybe you tell your boss, I can either do it fast and cheap, or I can do it cheap and high quality, but you can't pick all three. Nature doesn't do that. Nature picks all three. And that's why using this kind of math is very useful. It's also highly parallelizable, just like a lot of biology is. And so you get all three. You get quality, speed, and efficiency. And so when you put this together in trying to do analysis for files, it lets you focus on the unknown unknowns. We get a filter for the things that we really want to concentrate on and get to leave the rest behind. And so to work the 300,000 samples a day, we get about 20,000 new clusters a day. And 92% of the files that we take in or ingest are able to fit into established clusters, which means we don't have to go do work on that file because we know what it's going to do. We know it's like this other one that we've already analyzed. And so we have about another 8,000 files that are close to another cluster, and so we inherit their properties, which leaves us about 4.8% that we actually submit to sandboxes and third-party analysis. So this is a lot like coffee, right? If you took away the coffee from your department or your company, not much work would get done. But if you let people use coffee, it allows them to focus. And that's what we're doing here. The clustering lets us focus. It buys time to work on the things that are important, facilitates counting, it functions as an index or kind of sort, and it lets you triage your data. But the most important thing is that you get an asymmetric advantage. You remove your opponent's asymmetric advantage that they're using to polymorph the code so that it gets by our analysis techniques. And so once you've got a bunch of clusters, you can, as we've shown earlier, you can look at the clusters and find the areas that are not changing. And from that, you can write a signature, right? And so we have a whole bunch of devices. These companies are companies that provide, and there's many more, that provide capabilities for ingesting Yara signatures. And so if you want to produce Yara signatures, or if you use these organizations, you can take Yara signatures and consume them. And so our current research has been around trying to produce more Yara signatures. And I'll show you some examples where we can't. It doesn't work in every case, but we can still cluster them. We're trying to get down to 150 microseconds per core, per sample, which would be about a quarter of an infojoule. And let me put, an infojoule is about the same amount of, if we measure it in calories, like food, right? So if we want to map those two, there's about 4,000 calories in a joule. Or maybe I've got that backwards. It's 4 joules per calorie. Well, I'm sure somebody will look it up and correct me. Yeah? Did I get it? And so if we wanted to relate an infojoule to a piece of food, it would be roughly, if you could flake the skin off of an almond, it would be part of that. And so that's not bad to make a decision if you're trying to relate it to the heat value in food or kilocalorie. So I'm going to leave you with this one, which is my last little movie. This is a Win32 virus that likes to infect your LAN and move through your network, and then it's used to DDoS websites. And you can see it's pretty complicated on how they move this stuff around. It's also not well detected, and there's thousands of these new a day. But if we can cluster them, it saves us work. I just think it's one of the more interesting looking viruses. And so with that, there's my contact details. Thank you.
Feel this heat, don't feel like